Welcome to our deep dive on production readiness for large language model applications. In this video, we'll explore the essential practices and architectural patterns that ensure your LLM deployments are robust, secure, and scalable. From logging and monitoring to prompt versioning, CI/CD, and deployment strategies, we'll cover the critical elements that make enterprise AI systems reliable in real-world environments. Whether you're a developer, architect, or operations engineer, these insights will help you build and maintain high-quality LLM-powered solutions. Let's start by understanding why observability and traceability are foundational for production AI. OpenInference is an open standard that extends OpenTelemetry, specifically designed to trace and capture the behavior of LLM applications. It enables standardized tracking of crucial metadata such as prompt inputs, token counts, latency, and tool calls. By integrating with monitoring systems like Phoenix, Datadog, or new Relic, OpenInference provides deep visibility into how your LLMs operate in production. This level of observability is vital for debugging, performance tuning, and ensuring compliance with enterprise requirements. Let's see why this matters for your AI stack. Enterprise environments, prompt versioning is crucial for managing changes and ensuring reproducibility. Prompts should be decoupled from application code and treated as configurations. Store them in Git repositories or specialized registries like LangSmith or weights and biases prompts. Use semantic versioning such as v120 and tag production-ready prompts with a production label. This approach allows prompts to be dynamically fetched via an API, supporting safe updates and rollbacks. Proper versioning ensures that you can track changes and maintain consistency across deployments. Storing LLM conversation logs strictly in relational databases like PostgreSQL can be problematic for production tracing. These databases struggle with the highly variable and nested nature of agentic steps, such as chains, recursive tool calls, and child spans. Distributed tracing systems or document stores are much better suited for visualizing execution trees and parent-child relationships. They allow you to capture the full context of each interaction, making debugging and performance analysis far more effective. Guardrails frameworks such as NeMo Guardrails or Guardrails AI act as middleware layers within your LLM architecture. They function as reverse proxies sitting right before the LLM input and after the LLM output. Their role is to intercept and validate data, ensuring safety, blocking PII leaks, checking for prompt injection, and verifying formatting before passing payloads forward. This extra layer of protection is essential for maintaining trust and compliance in production AI systems. Protecting personally identifiable information, PII, is a top priority in production LLM pipelines. Implement an anonymization pipeline such as Microsoft Presidio before any data leaves your system boundary. Replace sensitive entities like names or credit cards with pseudonyms or hashes. When the LLM returns a response, de-anonymize the output by mapping tokens back using a secure internal state map. This approach ensures privacy while allowing for accurate and safe data processing. LLM router or gateway, like Kong, LLM, or Portkey, standardizes multiple upstream provider models behind a single uniform API. It manages automatic retries, fallback options, load balancing across API keys, cost tracking, and global rate limiting. This centralization simplifies integration and enhances reliability, ensuring that your application can seamlessly switch providers or handle failures without disruption. Automated regression testing for prompts is essential in a CI/CD pipeline. Set up a GitHub action that triggers whenever a pull request modifies any prompt file. The workflow runs an evaluation script, testing the new prompt version against a small representative dataset using an LLM as a judge. If the evaluation scores drop below an established baseline, the build fails, preventing problematic prompts from reaching production. This process ensures prompt quality and stability. LLM is an open-source LLM serving engine designed for high throughput and local model deployments. Its core innovation, page attention, manages attention key value memory similarly to virtual memory paging in operating systems. This eliminates fragmentation, allowing multiple requests to share memory efficiently, and boosting throughput up to 24 times over standard pipelines. The LLM is ideal for organizations needing fast, scalable LLM inference on premises. Semantic drift occurs when the distribution of real-world user queries changes over time, such as new trends or broken features. To monitor this, extract embeddings from incoming user queries and calculate a moving average of their vector space distribution. If the distance from the baseline shifts dramatically, trigger an alert. This proactive monitoring helps you detect and respond to changes in user behavior or model performance quickly. Protecting your API budgets in internal LLM applications requires effective rate limiting. Instead of simply counting requests, implement a token bucket or leaky bucket algorithm at the API gateway layer. This approach bases limits on the total estimated tokens consumed, including both prompt and output tokens, since requests can vary widely in size. Token-based rate limiting ensures fair usage and prevents unexpected cost overrun. Understanding the architectural differences between synchronous REST endpoints and WebSockets is key for LLM chatbots. REST is stateless and not ideal for long-lived streaming responses, as it relies on chunk transfer encoding over extended HTTP connections. In contrast, WebSockets provide persistent, bidirectional communication, making them perfect for interactive agents that need constant state updates and interruption signaling, such as stopping the agent mid-generation. Cold start problem arises in LLM microservices when serverless container infrastructures spin up new instances that must pull and load large model weight files into GPU memory before serving requests. This can cause significant delays. To mitigate cold starts, use dedicated always-on provisioning, cache model weights on shared network file systems, or leverage highly optimized base engine. These strategies help ensure your LLMs are ready to serve traffic with minimal latency. Horizontal scaling for vector databases like Pinecone, Milvus, or Qdrant is essential for handling large-scale AI workloads. This is achieved through data sharding, which splits the vector index across multiple nodes based on ID ranges or collections, and replica pooling, which duplicates shards to handle concurrent read queries without increasing search latency. These techniques ensure your vector search infrastructure remains fast and reliable as your data grows. Robust fallback strategy is critical for resilient LLM system design. If your primary API, such as Claude 3.5, hits a rate limit or returns an error, follow a tiered approach. First, retry with exponential backoff. Next, fail over to an equivalent model on a different cloud provider. Then fall back to a lightweight, highly available open-source model. And finally, return a polite, pre-composed UI error state if all else fails. This ensures continuous service and a smooth user experience. Tracing individual agent spans is crucial for debugging complex LLM applications. Agents can call multiple tools and make several internal calls before returning an answer. Without discrete spans, you only see the initial prompt and the final failure, making it impossible to pinpoint the root cause, whether it's a tool output error, a formatting issue, or an orchestration bug. Proper tracing provides the visibility needed for effective troubleshooting. Configuring the right metrics on a Grafana dashboard is essential for monitoring LLM applications. At the system level, track GPU memory utilization, API gateway request rates, and error rates such as 4xx and 5xx codes. At the AI level, monitor input and output token counts per minute, average latency distributions, semantic cache hit rates, and cost per user metrics. These insights help you maintain performance, control costs, and quickly detect issues. Blue-green deployment is a powerful strategy for updating LLM applications with minimal downtime. Maintain two identical production environments. Blue runs the active model or prompt, while green receives the new version. Automated end-to-end tests are run against green, and once they pass, router traffic is switched instantly. This approach allows for safe rollbacks if live metrics degrade, ensuring a seamless user experience during updates. Exposing internal databases to LLMs via tool calling must be done securely. Create an isolated read-only middle layer or API, and never allow the LLM to generate raw SQL text like drop or update statements. Instead, the model should call parameterized APIs such as fetch product by ID. The backend validates and sanitizes parameters before querying the data warehouse, preventing unauthorized access or data corruption. Retrieval augmented generation (RAG) chunk versioning is essential when your knowledge-based documents change. Each document chunk is tagged with a timestamp or hash. When a document is modified, old chunks are purged and new ones are indexed, ensuring the model never retrieves conflicting or stale information. This process maintains the accuracy and relevance of your LLM's responses. Comprehensive logging is the backbone of observability in production LLM systems. Capture detailed logs for every request, including prompt inputs, outputs, errors, and system metrics. Structured logs make it easier to trace issues, analyze trends, and comply with audit requirements. Integrate your logging with centralized platforms for real-time monitoring and alerting. Effective monitoring pipelines are essential for production readiness. Use tools like OpenTelemetry and OpenInference to collect metrics and traces from every stage of your LLM workflow. Feed this data into dashboards and alerting systems, enabling proactive detection of anomalies, bottlenecks, or failures. Continuous monitoring ensures your AI systems remain healthy and performant. Continuous integration and continuous deployment (CI/CD) are vital for rapid, reliable LLM application updates. Automate testing, validation, and deployment steps to catch issues early and reduce manual errors. Integrate prompt regression tests, security checks, and performance benchmarks into your pipeline. This ensures that only high-quality, production-ready changes reach your users. Dynamic prompt fetching allows your LLM applications to retrieve the latest prompt versions at runtime. By storing prompts in registries and tagging them appropriately, your system can fetch production-ready prompts via API calls. This flexibility supports rapid iteration, rollback, and experimentation without redeploying the entire application. Semantic versioning is a systematic way to manage prompt and model versions. Each version is labeled with a major, minor, and patch number, e.g., v120, reflecting the scope of changes. This approach makes it easy to track updates, understand compatibility, and coordinate deployments across teams. Semantic versioning is a best practice for maintaining clarity and control in enterprise AI projects. Tagging prompts and models as production is a simple but powerful practice. It clearly distinguishes stable, tested assets from experimental or development versions. Automated systems can then fetch only production-tagged resources, reducing the risk of deploying untested changes. This tagging system supports safe, predictable releases. Distributed tracing systems provide a holistic view of LLM application workflows. They capture the flow of requests across services, visualize execution trees, and map parent-child relationships between operations. This visibility is invaluable for diagnosing performance issues, understanding dependencies, and optimizing complex AI pipelines. Document stores are often better than relational databases for storing LLM conversation logs. Their flexible, schemaless structure accommodates the variable and nested nature of agentic steps. This makes it easier to query, analyze, and visualize complex interactions, supporting advanced debugging and analytics. Middleware layers such as Guardrails frameworks are essential for enforcing safety and compliance in LLM applications. By intercepting requests and responses, they can validate data, block sensitive information, and ensure proper formatting. Middleware acts as a gatekeeper, reducing the risk of security breaches or policy violations. Anonymization pipelines are critical for protecting user privacy in LLM workflows. Tools like Microsoft Presidio scan data for sensitive entities and replace them with pseudonyms or hashes before processing. This ensures that no personally identifiable information leaves your system, supporting compliance with privacy regulations. After processing data with an LLM, it's often necessary to de-anonymize the output. Use a secure internal state map to translate pseudonyms or hashes back to their original values. This process must be tightly controlled to prevent leaks, ensuring that only authorized systems can access the mapping. API gateways play a central role in LLM architectures. They unify access to multiple provider models, handle retries and failovers, balance load across API keys, and enforce global rate limits. By centralizing these controls, gateways simplify integration and enhance reliability for enterprise AI applications. Tracking costs is essential for managing LLM usage in production. Gateways and monitoring systems can log token consumption, API usage, and per-user costs. These metrics help you optimize resource allocation, forecast expenses, and prevent budget overruns. Global rate limiting protects your LLM infrastructure from overload and abuse. By implementing token-based limits at the gateway layer, you ensure fair usage across all clients and prevent any single user or team from exhausting your API budgets. This is especially important for shared enterprise environments. Automated prompt evaluation often uses an LLM as a judge. This approach runs a small, representative dataset through the new prompt version and scores the outputs. If the results fall below a set baseline, the change is blocked from production. This method ensures that only high-quality prompts are deployed. Enforcing baseline scores in prompt regression testing is key to maintaining quality. If a new prompt version underperforms, the CI/CD pipeline fails the build, preventing regressions from reaching production. This automated safeguard keeps your LLM outputs consistent and reliable. Age detention, the core of VLLM, revolutionizes memory management for LLM inference. By managing attention key value memory like virtual memory paging, it eliminates fragmentation and allows multiple requests to share memory efficiently. This innovation dramatically increases throughput, making local deployments much more scalable. Optimizing throughput is a major goal for production LLM deployments. Techniques like memory sharing, efficient batching, and advanced scheduling help maximize the number of requests your system can handle. High throughput reduces latency and improves user experience, especially in high-demand environments. Detecting semantic drift is crucial for maintaining model relevance. By continuously analyzing the vector space distribution of user queries, you can spot shifts in user behavior or emerging trends. Early detection allows you to retrain or adjust your models proactively, keeping your AI aligned with real-world needs. Automated alerting on semantic drift ensures you're notified as soon as significant changes occur. Set thresholds for acceptable distance from the baseline and configure your monitoring system to trigger alerts when these are exceeded. This enables rapid response and minimizes the risk of degraded model performance. Tracking token consumption is more accurate than counting requests for rate limiting. By monitoring both prompt and output tokens, you can allocate resources fairly and prevent abuse. This approach is especially important for LLMs where requests can vary greatly in size and cost. Choosing between synchronous REST APIs and streaming WebSockets depends on your LLM use case. REST is simple and stateless but not ideal for long, interactive sessions. WebSockets support persistent, real-time communication, making them better for chatbots and agents that require ongoing interaction and state management. WebSockets provide persistent, bidirectional connections that enable real-time updates and interruption signaling. This is especially useful for LLM agents that need to update state or stop generation mid-process. Persistent connections enhance interactivity and responsiveness in AI-powered applications. To mitigate cold starts in LLM microservices, use dedicated always-on instances, cache model waits on shared file systems, or choose highly optimized base engines. These strategies reduce startup latency, ensuring your models are ready to serve traffic without delay, even during peak demand. Summary: production readiness for LLM applications involves robust logging, monitoring, prompt versioning, secure data handling, and resilient deployment strategies. By following these best practices, such as using OpenInference, implementing guardrails, automating regression testing, and optimizing for scale, you can ensure your AI systems are reliable, secure, and ready for enterprise use. Stay proactive, monitor continuously, and iterate rapidly to keep your LLM deployments at the cutting edge.